Hey everybody. Today we're talking about matrices and doing some matrix arithmetic. In mathematics, a matrix is just an array of numbers. Here's a couple of examples. We describe the dimensions of the matrix by putting the number of rows first, followed by the number of columns. So B, for example, here is a 3 by 4 matrix. A matrix that only has one row sometimes gets called a row matrix, and a matrix that only has one column sometimes gets called a column matrix. Sometimes those also get called row vectors and column vectors for reasons that I think are pretty obvious. In those cases, sometimes we'll even use vector notation with the little arrows over them, or sometimes writing the lowercase letters in boldface. In general, though, we give matrices the names of uppercase letters, like capital A and capital B. And we'll reserve the corresponding lowercase letters for their entries. In particular, we can use double subscripts to say which entry we want from that matrix. So here's matrix capital B again. B sub 1, 4 is going to be the entry in the first row and fourth column, in this case 2. And B sub 3, 2 is going to be the entry in the third row and second column, which in this case is 4. Sometimes we'll write curly braces around B sub ij to denote the entire matrix capital B, the matrix whose entries are B sub ij. Matrices are equal if they have the same dimension and all of the entries of the matrices are the same. If we swap the rows and columns of a matrix, we get the transpose. So our matrix B here on the left has transpose there on the right. The first row of B is the first column of B transpose, and so on. Notice the notation. We wrote the t as if it were an exponent, and that just means the transpose. By the way, if you're taking the transpose of an m by n matrix, the result is an n by m matrix. So not only are the rows and columns reversed, the number of rows and columns are also flipped. Of course, if you have a row vector, the transpose is going to be a column vector, and vice versa. We can do addition and subtraction of matrices, but only when they have the same dimensions. And in that case, we just add and subtract the corresponding entries. Here's an example of what I'm talking about. For example, I'm going to get that 2, the first row in the first column of the result, by taking the corresponding entries 6 and 4 and subtracting them on the left-hand side. Similarly, for the first row and second column, 2 minus negative 2 is 4, and so on. If you have two matrices with different dimensions, then the sum and difference are not defined, as in this example. This subtraction problem does not have an answer. When we're dealing with matrices, we call individual numbers scalars to differentiate those objects from the matrices themselves. The most obvious scalars when you're dealing with matrices are actually just the entries in the matrix. The name for the terminology, scalar, is simple. If you multiply a number, a scalar, by a matrix, you're going to multiply that scalar by every entry in the matrix. In other words, you're just scaling the matrix. For instance, 2 times 6231 is 12462. I've multiplied every element of that matrix by 2. Let's do a few more examples. Here are two matrices, A and B. A is 3 by 2 and B is 2 by 3. If defined, I want to compute A plus B, A transpose plus B, and A minus 3B transpose. A plus B is not defined. These matrices have different dimensions, and so we cannot add them. However, if we take the transpose of A first to give us a 2 by 3 matrix, then we can add. We can add both of these by adding the corresponding elements, and here's what we get. Finally, let's do A minus 3 transpose of B. Okay, so here we need to respect order of operations. And the order of operations is fairly easy to remember here because of the exponent notation on the transpose. We're going to treat that transpose operation as if it were an exponent when we're thinking about order of operations. And then we're just going to follow PEMDAS. We'll do the transpose first, and then do the multiplication. So doing 3 times that entire second matrix, multiplying each of the elements by 3. And then I just subtract. Overall, I get 3, -5, 0, -2, -5, 15.